graduated from UBC with a BS in Geophysics and Physics in 1971. He then spent 27 years with Hitachi HP Minerals Company, during which time as chief geophysicist. He campaigned BHP's programs in airborne geophysics, which resulted in the development of ZTEM and Falcon technologies. Then in 1999, Ken helped with a technology-focused service company that specializes in the application of innovative processing and data analysis to help drive the discovery of new mineral deposits. Let's welcome Ken Witherly. Thank you.
Thanks, Megan. Good morning, everybody. You noticed halfway through Thomas's talk, they actually turned on the microphone. Excellent. You must have got your check cleared or something like that. Just as an observation, I guess, from the talks this morning, and I know there's a distinguished geologist right at the front table with me. I call it the Ebola table, but somebody else joined me. I see a lot of information in our geophysical surveys that we really don't have very good geological explanations for. And I think we're probably pushing that even more with more 3D inversions. We see things that, as you know, everything from Peter Fulligar's, the sort of geology morphing over time in our own camp, the difficulties of getting proper constraint calibrations. I've heard, you know, we have a number of clients that'll like a puppy, they'll bring the torn newspaper of all these mag sus data readings that they've acquired over all the years. And you say, what have you done with them? Have you plotted them up in your sections? Oh no, it's geophysical data. We're expecting you to tell us what to do with this. And you put it into your model and you look at it and you say, I don't know what's going on with this. It's either too much in one area or not enough over a large area. But you know, I think we just have to keep pressing on, and we are an observational science. The strength of what we do is we can see things that to a first order are often invisible through normal geological evidence, even drilling, because we all know the difficulties of having a little piece of core to try and explain something that really geologically is probably often kilometers in size, just like Sid's shots. You know, all those things he has. You know, he didn't show too many geological maps. The ones that were there are pretty bloody basic. And of course, they kind of end at the 2D. There's not really a lot of 3D. They get their ore body, but they don't really understand a lot about the structure and alteration. But certainly you could see in those images, there had to be issues that were mapping things that clearly are geological, but we're not quite prepared to say exactly what they are, because geophysicists, we know, are inherently extremely modest. And we don't like to push ourselves into the geological world too aggressively. It's like a presidential debate, right? You have to watch your audience. This is a great slide. Let's say great slide. It's an image that I swiped from a paper that Jeremy Richards co-authored and Martin Unsworth on. I've just pointed out to you. It actually appeared in Geophysics Interpretation. Anyways, it was an introduction that I liked because it had a variety of geophysical responses, susceptibility, density, resistivity, chargeability, and geological effects for basically a buried porphyry system. This was some NSERC work that Geotech participated in, and I think Jerry Carlson. That paper came out just about a year ago, and I looked at the abstract that they presented at the SEG a couple of years before that, and certainly the paper's much better, so I certainly point people to that. So we're going to be talking about, and thanks for Thomas to doing the great technical introduction of ZTEM. I didn't even have that, but it's nice to have as a background. So we had the opportunity to look at data from two deposits, two porphyries, one in British Columbia, the far north end of the Quesnel terrain, and another down in the heart of Porphyry district in Arizona. And they're quite different in response, and I think this is still part of what we have to expect, even though, you know, we're touting a technique like ZTEM as being applicable to porphyries. There's no set response. It's not like going out and maybe looking for a magnetic nickel deposit in the Sudbury Basin, where because they've worked there for decades, they have a pretty good idea of what they're going to find, the size, the conductivity, even the stratigraphic location. Porphyries are still, there's a lot to be learned. And one of the things as well here, and I say won't, not to berate anybody, but when we got into some of these areas, particularly in British Columbia, there's a lot of data there that's never been looked at. A lot of data. And there's some stories in there that I think are important from the point of view of helping guide exploration in these environments. But I think we're still struggling as a community to know what to do with that. So, anyways, first one, the Kemess deposit. It's as you say, it's up in the north. Here's the Quesnel terrain. So here, it's up at the northwest end of that. There's a number of porphyry systems located in that. They sit around about a 200 million year age. In the particular, I'm torn between the screen I can read and the microphone. But there were two significant deposits in this camp. There was the Kemess South deposit, which was mined for a period of time, and they pulled out about 220 million tons, some pretty good gold, and of course copper grades. Not the hypogene grades here in British Columbia aren't stellar, right there. But if it's shallow and you've got some gold, you can make some money on it, and I think they did. They then went ahead and attempted to permit up here what they call Kemess North, and that was sort of in the 06, 07 range. And the company, I think it was Northgate at the time, got their environmental permit knocked back, and they had one of these Falconbridge hissy fits, and they left the province for a while. And that resulted in a big dent in their knowledge of the system. They actually lost a bunch of data at that point, but they've come back under a new name, Orico. And in a couple of years ago, they flew a ZTEM survey over the whole area, and we got a chance to work on this data after the roundup earlier this year, just to say, well, okay, we don't know a lot about this system. We worked on a few other porphyries in other parts of British Columbia. Always the Mount Milligan is public domain. There were a few others that we put out, and a few other groups. Mira worked on one as well in the Huckleberry area, I think it was. But here's always the all-important magnetic data over the area. Here's the Kemess North, and there's a decent resource there. But because of their issues with the open pit, they're refocusing to a potential underground opportunity. And so there's sort of the term, as in the last slide, was both a Kemess North as well as a Kemess Underground. And they're looking at a higher grade portion of that sits over the eastern part of the old open pit idea, but the ore body is extending off sort of to the east, but it's also getting deeper. There's the location of the Kemess South deposit, now mined out. And certainly from the first order, when you look at the magnetics, one's blue and one's red. And that was quite interesting to us. There's a few people who have commented about remnants. And it certainly, to me, the geological information and remnants is quite interesting because, as Peter said, most of our careers, geophysicists have taken the role of expunging this evil remnants from the data because it doesn't contour properly, it doesn't invert properly. Whereas in fact, actually for me, it's a timestamp. It's showing there's something different in time occurred. And if it correlates with mineralization, that's even more interesting. And we actually did some discrete body modeling using a product, Model Vision Pro, that's handled now by Tensor. And we can see that actually shapes up as a discrete remnant body, whereas the feature up here, the Kemess North, is not. So it's immediately sort of breaks apart the idea that maybe there's some sort of structural offset. You can see a northwest grain through here, that these probably, while they both share the same first name, they probably have a difference in time when they originated. And that's something the geologists, I don't believe, actually knew. I don't believe they knew that. So anyways, but this is a ZTEM talk. Here's some of the images. Thomas introduced these. The middle one is the total derivative. That tends to be the higher frequency. It's less filtered. It tends to show a little more noise, but it's often got the greatest resolution. So it's one of these trade-off sort of things. If you can deal with the noise, The DT image is probably the best for shallow sources. And then the total phase rotated is the one on the right. So here's the DT. And then we produce a product that looks a bit more filtered, but sometimes that's better from a bulk averaging. And it's a connectivity calculation that our consultant Daniel Sattel worked up with a colleague in Germany that gives us a little better what we think is apparent resistivity results with that. But you can certainly see, major connectivity zone associated with Kemess North, also something definitely around Kemess South, and structures going off to the east. These are not mapped, okay? These are not things that are well understood at all geologically. The grain to the northwest, that shows up in the mag. Everybody's on the same page. There's something going on in that direction. They talk about northeasterlies, but they haven't really been able to constrain them very well with the mapping. And this isn't a particularly evil terrain. I mean, there's some mountains, there's some flat areas, some river bottoms. There's a lake over in here. I think that was part of the reason why their environmental permit got knocked back. Might be a great place for salmon breeding, I don't know. But anyways, and this is often what in plan images with the ZTEM we expect to see is structure. And then sometimes in between the structure, we'll see things that seem to have a resistivity character that then you start saying, is that an intrusive? Is that background? What's really going on with your data? We see some features in here. There's no mineralization in here, and this is actually excavated. Is there an effect from the actual excavation? Personally, I don't think so. There were some tests with Aerotem that the Geoscience BC people did around the Grand Isle deposit. I think maybe they were seeing acid mine water in the bottom of the pit in that particular case. In this case, I think we're seeing probably primary geology. Here's a little more detailed look at some of the structures that we, bravely, foolishly put down on the image. At this point, the client's current interest is very much focused with drilling up in this area in here. There really was no mandate to go back to look at the regional geology. That was actually done by, I believe, a master's student at MDRU, 2006. That fellow's moved on. He's now working in Sudbury. I don't think he worries about the Cordilleran anymore. Might be like to go back to it, but so we've got information. We're not quite sure what to do with it. We have data that's not information as well, which is always frustrating. When we look at some of the 3D models we produced from this, interesting character here. There's two east-west lines. They're shown here in this cartoon. There's a line across here and a line across here. They should actually show them as north-south. Oh, there's also lines east-west. We didn't put them all in. So there's Kemess North. You can see the line across there. And so the unmined porphyry system and that depth range is, we're dealing with 500 meters down, so 2,000 to 1,500 meters. So it looks like the porphyry system sits in a relatively conductive slab, and then a very large resistive body starting around 600 to 700 meters. This was validated, as best as we could call it validated, with a Titan survey done in 2006 to 2007. It caught a piece of that resistivity feature here. So it looks like, are we talking about a thrust relationship or a post-mineral intrusion that's come up and almost breached or taken out the porphyry system? Don't really know, because there's not really a lot of drilling down in this environment. The mineralization, we know, sits up here, shallow depth, but it also seems to be plunging or dipping down off to the east. This one actually is a north-south section, so we had a mixture. The one east-west, and then this one links Kemess North. You can see that resistivity feature here. Now looking to the south, over Kemess South, you can see this appears to be dipping down this resistive zone. Very unusual, not the normal sort of thing that we normally think these things are sort of subvertical by and large, because we often lack any data other than geophysical images. We have done Mag 3D modeling here, but that's not part of the story I'm going to have time to show today. We've got some other interesting data that was acquired over this. We have radiometrics, potassium anomalies that were acquired well over 15 years ago, not really stared at very much. We can see the Kemess North deposit here in south. There is a radiometric. This is the Russian hackers. No Hillary email here, sorry. So that, it looks good. I mean, you know, from a point of view of distinct anomalies, there seems to be a discrete one with Kemess South, although the feature with Kemess North is far broader. And what do you do about that? Well, it's just often the nature of how these things, you know, what nature gives us. Here's a shot. This was an interesting one for us, and I'm sure Sid would appreciate that. Strange IP survey from 1992. We seem to have Kemess South, Kemess North, and this is my design here. This big ellipsoidal feature. But we've got something that seems to be about 8 kilometers north-south. Somehow seems to link the two together, but there's no geological model for this. This is just sort of this data was actually kind of lost in the BC Department assessment files, and the client, to their credit, is now trying to recapture this off of paper maps and put it back into a digital environment. It's only 50-meter dipole, N1 through 4, but it's probably the best alteration mapping we have for the property, because the Titan work was all focused up at the north end around Kemess North. And you know, we actually see an IP anomaly off the east side of Kemess South, and then there's a fairly strong feature associated with Kemess North that extends off, unfortunately, down towards the lake. Radiometric response there, potassium, just repeating that one again, and then one of the 180 TPR with the structure. So, interesting. The product on the left is one of the things we've started to introduce, because we found many of our clients, we're talking all through the scales, whether ranked juniors with one accountant and one lawyer, right up to majors, aren't doing as good a job with their geological mapping as is needed in most cases. It's in part a question of talent, it's in part a question of time. But with our geophysical data, if we're prepared to stand there and demonstrate a process, we can create a product that probably captures, quite often, 80 to 90% of the value that a surface geological map will have. It is magnetics data, but we can characterize structure and lithologies in ways that are extremely powerful, because we have a uniform sample to draw from, not one outcrop every half a kilometer, whether that's available or by choice and time. I've encountered a number of cases where we bump into the geological map on the property, and you look at the geophysics, and as Sid said, sometimes they're often going 90 degrees, and nobody has an answer for that. Nobody takes ownership of that anymore. So we've started to generate this product. We're trying to make some money on it. It takes far too long because it's very labor intensive, but it's an extremely powerful way to get geology, I think, back into the story, at least some form. And if a geologist wants to critique it and change it and reinterpret it, that's great. But at least there's something on the table. So that's the Kemess summary. We see conductive structures, which we believe to be major faults and contacts. There's definitely correlating with the mineralization, so that seems to be important. What they are physically, it's unclear at this point. We have some correlation with the magnetics, but the magnetics in this case is not as clear, although it does show the overall structural grain. High potassium values showing alteration effects. That looks quite interesting, courtesy of the GSC in this case. And I think, you know, what we can get out of the magnetics and ZTEM data could be extremely valuable. Hopefully this just didn't come at the 11th hour in this project, because they're at the point where they actually have to, the current company has to make a go of it, or they're probably going to abandon it and, you know, focus on something else. So now for something completely different, not in a Monty Python sense. We've dropped down into Arizona, into the heart of old Porphyry country. And we've got a survey that was done over an area around the Resolution deposit, which is probably, I believe, the largest undeveloped porphyry in North America and highest grade. It's deep. It's parts of it are well over 1 kilometer in depth. And it was one of these ones where people said, oh, it was found in 1992, and then you go back and say, yeah, but somebody drilled it. Somebody drilled into that like in the 70s. They just didn't quite recognize it. It's a story that, like the UTSA, has evolved over time. And now, Rio Tinto and their partner BHP are getting very serious at looking at potential development, but underground temperatures, I believe there's some 60 degrees C down where the ore body is. It's not going to be an easy thing to mine. But anyways, the geophysical story. And this was put together by a geologist, this part of the presentation. So he only let things through the filter that he believes were geologically reliable. This is not, the geophysicist did the processing, but the geologist actually assembled the story, which is one of the firsts for us. But anyways, we believe he's done us well. Motivation. Why run a ZTEM survey over this? Just for the heck of it? Because Geotech says it's a good idea? In this case, 2005, I believe, or 6. The data were shown in 2007. An MT survey, I believe, is sort of the order of 6 to 8 lines were run over the resolution. Here's the resolution dash outline of the deposit. I think that's sort of like a 1, and there's a 1.5% copper grade. This is a vertical section. We're looking down from, that's topping out at about 1,200 meters. Surface here is nominally a kilometer. And so we see this, what was presented as an unconstrained MT inversion on one line. No location was given, one line. And then what's called a constrained inversion, which gets this overlying conductive sediment, seems to pin it, so assuming they had some drill holes here. And then the resolution feature itself, as we'd call it, ends up being kind of this chimney and then seemingly broadening out of depth, which of course, geophysical anomalies that broaden out in depth are no surprise to anybody. What we didn't have at the time when that was presented, here is an outline of the sulfides in the system. So these kind of contours here and here would sort of correlate with that. So you can see it's a lot of pyrite in the system. They're calling 7 to 14%. So in this case, probably the explanation for the conductor. And this is the geological section in here. There's the 1% pyrite shell, or copper shell sitting in here. So we tried to get the scales as close together as possible. So this was the motivation to say, let's go try a deep penetrating EM system. Well, of course, it wasn't for us. It was for the people that did it. Here's a shot looking eastward. It's a fairly topographically challenging area, so some of the things Thomas said about being able to do a loose drape with the system is beneficial. We're not trying to hug rugged terrain with a active source time domain system, which would be safety-wise and other things probably pretty challenging. Magnetics, interesting story. Well, of course, in the U.S. it's the sad story. Our basic national database sucks. And we've got better coverage on Mars than we do on our own, bloody U.S. It's really, Matt Damon loves that, right? So here's resolution on the standard USGS stuff. Here's a little better. They've added to it in ⁻76, improved it a bit. And this little insert here is basically the coverage that we got from the ZTEM survey, stuck into that earlier '76, or we call it the Freeport. Freeport was the client who acquired the data set in 2013 and say this is the magnetics data that was a result of that. So the mag is a very interesting story in this environment, but it's not the story for today. But we do show it because getting good mag data is always helpful. Here's a blow up. They couldn't fly over the town of Superior, so that's been whited out. There's the resolution deposit. You can see a titillating magnetic low. This is an RTP image sitting in here. We did naturally Mag 3D modeling with this, unconstrained. We had, other than published information, we were provided nothing in terms of the geology. We had to draw only from the public domain. And so maybe an alteration feature here, and then that something's continuing up to the northeast. And there's, it looks to be geologic. Anyways, mag's good, always good. Now, this is the environment that we worked in. All of the white areas had to be removed because of very, very, very aggressive power line. They're coming in from this direction here. There's like 3 big towers. And it really knocked out a huge amount of the data. So we spent a lot of time making sure that when our inversions were finally done, we were reasonably happy that they met geological sense as well as geophysical criteria for signal to noise. It took us about 3 iterations. The 2D are easy, right? You just cut things out, mask things. But with the 3D, you need space to get proper inversion. You can see we didn't have a lot of terrain. This little island, this little peninsula that the resolution sits on, we actually felt that that data was okay, but we had to do some interesting jumping over stones to get to that point. But then the geologist was the one who said, yeah, I think what you've done is okay, and I think what I'm seeing is geology. But it wasn't trivial, and that's one of the weaknesses we found with the ZTEM, is it tends to be quite responsive to power line effects. Here's a shot. I think the bottom one, it's a pseudo 3D cross section. So here's the plan map outline projected downwards, and we see the ore shells in here. Here is the conductivity body derived at 2 isosurfaces from the ZTEM anomaly. And so we're getting, and there's a plan section in there sitting over top of that. So all of these are sort of interrelated, but this probably is the easiest one to absorb at this point. In our formal presentation, we had sort of an animation of a whole series of these, but for the time I have, had to cut it down to sort of the basic thing. But we ended up with a body that, yes, it looks bigger. There's the ore shell here, with the pyrite sitting over top of that. And we have this conductivity lozenge. It extends. I think we'll have one here. Here we go. We have this body here. Here's the resolution outline. So we have this conductive zone through here. It overlaps and gets thicker, bigger over the actual resolution area itself, although it's not a one-to-one mapping of what's called the deposit. We never really expect that, but I mean, this is like horseshoes or hand grenades. If you're close, you're probably doing as good as you're going to get. We think this anomaly could be contamination, and it was flagged as such from the power line. We left it in because it seems to be close to where the mineralization is. There's another, I think, vein type system just up to the north in here. But that was the sort of recovery that we were able to come up with. An anomaly is that spatially fits reasonably well within the defined, that we could locate public domain information as to where the ore body is. So we were pretty pleased with that. Thanks to Rich Lavelle at FMX, who were the group who actually flew it. I had a number of good conversations with Donald Hinks, Rio Tinto Expiration in Salt Lake, about what some of these anomalies could be coming from. It seems like it's obviously pyrite. When we say conductors here too, we're not talking about, as Scott mentioned, with the SAM system has got some similarities, right? It's a plane wave. You get detectability of current channeling effects, but you lose some of your ability to get good conductivity measurements. They're not as quantitative. And the word conductor in this case probably means something, we think, about 30 to 50 ohmmeters in rocks that are probably 2 to 500 ohmmeters. So it's not like a magmatic nickel system where you've got 100,000 Siemens conductor, but it's conductive enough to be picked up with this sort of system at a depth well over 1 kilometer. And with that, I'm going to just jump on to my next one. But I can take questions. I'll take questions.
Thanks. Questions for Ken? Yes.
2 comments. Ken, when you use the word current channeling, feel free to use the word anisotropy.
It's always on my mind, Sergio.
All right. Yeah.
As are you.
About time, you talk about timestamp. Years ago, we had an experiment in the Andes where we're using something easy, the analytic signal, and relating with the RTP, and we were getting a value where we're associating those values with the known date of intrusives. And we had a good results, and we were extrapolating that into known dated intrusives, and it was a good, cheap and good experiment. Yeah. About remanents, because we have been talking about remanents all this.
Right. Yeah. It should be shown more respect, I think. Not just asked to leave the room.
Yeah.
Understood. It has to be understood, I think,
Yeah.
is a value. So, yep.
Okay. I've got a couple of questions, but keep it brief. At Kemess, you suggested that mag low was remnants. In my experience, especially with porphyry systems, the nature of magnetite is it's normally pretty coarse-grained. And as we know, coarse-grained magnetite finds it very hard to hold on to remnant magnetization. All the little domains in it cancel each other out, right? And you rarely see, or what I would say, good evidence of a porphyry being remnant. So how convinced are you there that this is the case? Do you have any mineralogical support or petrophysical support for that interpretation?
It's observational in the geophysical sense. Seeing a bit of blue in a map doesn't mean there's remnants. You have to do some poking and prodding, do some forensics work. And there are cases where dipolar features, you're a bit surprised to see them, because one of the problems is we often RTP data before we even look at it. And so we've already started buggered things up a bit. I mean, RTP should help, but it also moves things around, and remnants doesn't behave well in that moving the chairs about. So you might have to go back to the original TMI, but what we've attempted to do, when I say observational, is go in and do some actual modeling on profiles. And we typically use model vision. It's not the only solution. And we say, okay, if we assumed it's all inductive effects, how does it line up? Does the modeling, because model vision is good about saying, no, there's a bit in here that doesn't actually fit. So you're going to have to either, the challenges of remnants often too is they can be in the same direction, and that's one of the problems, Peter, that we found when we were looking into it, is that if the remnants is in the same direction as the current induced field, then it makes your whole susceptibility exercise difficult, because those susceptibility measurements aren't aware of remnants, but if it's actually enhancing the response. So it's just another thing that comes to bite you in the bum. So in that particular case, we actually pulled apart that anomaly with model vision and satisfied ourselves. I forget what the Koisenberg ratio was, but we came up with something, a discrete body that remnants was required to, it fit very well. But it's a historical mining operation. I don't think any academic studies were done on it, no petrophysical work. There wouldn't be anything in the literature we can fall back to and say, give us any, it's a suspicion as opposed to a confirmation. Yeah.
Any more questions?
Well, my second question.
Okay.
At Kemess, sorry, not Kemess, at Resolution, in the section, in the constrained M10 version, the conductor is quite subvertical and linear, especially heading up towards the base of the base mineral cover. On your section, you showed a fair few faults coincident nearly with the location of that subvertical conductor. I'm wondering how much do you think the faults could be causing at least the top part of that conductor and not necessarily the large amounts of disseminated pyrite?
We didn't have any independent information in that regard. I assume that section was put together internally with Rio Tinto, so they added data that they had. I don't think we recovered that in the public domain information, but I mean, point taken, I mean, the structures could be contributing, but I mean, there are a lot of places where structures exist and they don't show up with quite the same degree. It's sort of a matter of, you know, is it weak, is it moderate, is it strong? And there seemed to be something else overriding it that suggested it had to be, it was much stronger, much more coherent response. So you sort of like, again, you kind of angle over in one direction, but it's not, you're not 100% sure, no.
Maybe Theo can answer.
Maybe I can't.
He'd have to kill you. Okay?
All right, well, thank you, Ken.
You're welcome. All right, they've given me a couple of minutes to talk about Expiration 17. I asked this at the Lalor one, and it was a disappointing, like, it was Greg Hodges and two others, but before you saw the slide, how many people have heard of Expiration 17? Oh, this is better, this is better. We actually have we have on our website, we've got these Google Analytics, and we had a meeting in Telecon in the middle of September, and Cameron, he's our Twitter genius, he says, he showed us, we're showing these analytics, and what was interesting, there were more people in Perth have hit the 17 site than Vancouver. So this is part of the motivation to come out here and give you a bit of a wind-up on it. It's going to be happening just a little over a year from now. This will be the sixth decennial conference. They were started in '67 by the GSC, and it's a great roundup of work in geophysics, geochemistry, remote sensing, information technology, and to be relevant with the times, integrating that in the geoscience environment with obviously a very strong component of geology. So we're trying to really do a good benchmarking of where technologies have gotten to in the past decade. There's always going to be some forward-looking component to it, but it's really quite, the purpose of these meetings historically has been to say, what's been developed in the last decade and how well does it work, and what can you actually use going forward with some confidence that it actually will deliver some results. And of course, sometimes its negative outcomes are just as important as well. So we have, there's two plenary sessions, the Monday and the Wednesday. It's a 3-day conference for the talks. We'll have keynote speakers from around the world giving highlights on the major developments in all the technical topics we're going to be looking at, state of the art. Then we break out on the Tuesday, that's the lower part of this, the session in here. There'll be a trade show, so any of you that want to hang up a shingle and have yarns with your colleagues from around the world about what your services are, feel free to do so. I'm involved with Cersei Lalonde on a case history section through here, but there'll be other breakout sessions. Mel's not going to be here. It'll be a couple of other gentlemen have kindly agreed to stand in. So that's the Tuesday. Will be these breakouts, and then the poster sessions. We'll have a number of those. Wednesday is another thematic session and the poster session. The exhibits, and then we're going to have a series of workshops before and after, and these are run by people that know a lot about these specific topics. I haven't put their names down here, but they'll be running on the Thursday morning, the 26th, and the Saturday, the 21st. So that actually the middle section should be above. That's going to be the before the conference starts. And then down here, should mention this one. This is kegs. is hosting Doug Oldenburg to give his disc talk. So that'll actually occupy all of that day after the conference. And there is a field school as well. We have limited enrollment possibilities, 20 we'll be able to put together. But Richard LaChapelle of Syntrex is organizing that, and there'll be, what happens there for 3 days, a series of service companies who are offering their time will take their equipment up and run over WD-16, one of the undeveloped shallow nickel deposits up in the Sudbury Basin. So that'll be before the conference as well. We think it's a great opportunity for people, particularly from overseas, or students that haven't maybe had as direct contact with some modern instrumentation. So there'll be field work during the day and data assessment at night, probably with some highlights of some of the work in, we're looking at doing a tour of Geotech's facility in Sudbury, their hangar, that seems like that's on, and maybe even Science North as well. So the whole footprint of the meeting from stem to stern will be about a week, with the core part on the Monday through the Wednesday. And we've tried not to conflict with anybody else, but there are, of course, a few. The guys in Montreal are going to be having their meeting the same week, but as they say, c'est la vie. So as part of the Expiration 17 events, we're going to be having an award for the Frank Arnott Prize. It's a contest that currently is ongoing. It's an open source. Basically, it's a bit like the Interra or the Gold Corp, but we don't have $1 million to hand out. We have a lot of fame and fortune and honors. And so on our website at the bottom there, frankarnottaward.com, the contest right now is data sets are available for download. We've got 5 sites from around the world. We've got incredibly good data sets for. 2 in Australia, 2 in Canada, and 1 in Finland, the Kevitsa deposit. And we have to know who's involved by the end of the first week of December. So the teams are now forming and working on data sets, and they have until the 8th of December to say that they're participating, but the final results don't have to be in until the end of March of next year. And then our judges will go through that, and we'll be making the awards. There will be a cash award. We have an early career, people 0 to 5 years out of uni, basically, and then a seasoned explorer award. So we figured that was the best way to put it together. So go on the website and have a look, and it's linked in with the 17 story. So thank you.
Thank you, Ben. All right.